AJ, I have to tell you that AJ is probably the leading greenhouse engineer in the U.S. right now. So that's why I invited him down to talk to us and help out with the in-service training. And so I appreciate him taking the time with us. And I'll let him give any further introduction he wants to for himself.
Okay, thank you. So when I prepared for this presentation, I looked up the Virginia Tech logo, and I noticed you have a date here, 1872. And so I put our date here, indicating that next year we're celebrating 250 years of Rutgers University. So we're a little bit ahead of Virginia Tech. You know, in academia we always try to outdo each other, right? So that's...
Thanks.
But I'm from Rutgers University. I've been in the US for over 25 years now. Got my training at the PhD level at Cornell with Professor Lou Albright, working on structures and environment, particularly greenhouse construction and greenhouse environment control. And I got a faculty position at Rutgers University in 2000. I've been working in the same area since. So today I'm going to talk about greenhouse heating. So we're going to review all the calculations that are the basis for virtual growing, which we're going to hear about tomorrow, I think, more than today. These are calculations that were put together by greenhouse engineers in the past. I would say the previous generation, people that have since retired. A lot of the information, I think, is based on empirical data. So it's hard to trace back exactly where a particular number or a particular approach came from. And that's sort of a challenge for us now when we want to try to put things in perspective, and particularly when we want to find out what the assumptions were that we used in the past to come up with some of the numbers that we use today. But that's what we have to work with. So I'd like to quickly review some of the heat exchange processes that are involved in greenhouse heating. And basically we worry about convection, conduction, and radiation. And you probably have some idea what all these different terms mean. Radiation, you think about solar radiation. Convection is when air is moving or water is moving in greenhouse systems. So we have a fluid or a media that moves from one place to the other. And in that process we can move heat from one location to the other. And then we have conduction, and that typically in greenhouses involves heat transport through structural elements from the inside to the outside, or if it's warmer outside than inside, it could be from the outside to the inside. So those processes are occurring and occurring simultaneously, and we try to capture those processes when we calculate the overall heat loss from the greenhouse that we then use to calculate the boiler capacity or the heater capacity that we need to try to make up for that heat loss, to try to maintain the specific set point temperature that we need for our crops. So in this sort of composite picture, you see these three processes in a sort of a very general greenhouse with different heating systems, floor heating, bench heating, unit heaters, hot water pipes, all kinds of systems. So this is not a realistic greenhouse, but tries to show you that for all these different greenhouse heating systems, we have these three different processes going on that we need to worry about. So a very busy picture trying to capture what is happening in greenhouses. So the crux of the matter is, how do we calculate how much heat a greenhouse is losing, because we want to calculate what the capacity should be of the heating system that can make up for that heat loss. And we do that by going through different steps. We have to calculate the structural heat loss, so a combination of the conduction and the convection heat loss, so structural heat loss to the structural elements, as well as air movement happening in and outside the greenhouse that carries heat away from the structure. We have infiltration heat loss, that is part of air movement, typically through unintended cracks and openings. We saw a lot of those in the greenhouse today, especially around ventilation windows, doors, and things like that. Sometimes we see them in the glazing material, particularly when you have older greenhouses that are made of smaller panes of glass that are lapped. Sometimes those panes of glass slip and you get nice cracks that allow air movement. And with that air movement, of course, we can lose heat. And so we need to take that into consideration. And then the third step we have to do is look at the perimeter heat loss. That's heat loss that's occurring along the bottom perimeter of a greenhouse, where the warm floor the warm soil in some cases is typically in direct contact with the very cold ground soil outside the greenhouse. If we don't have a barrier there, we can lose a fair amount of heat to the outside. And we saw some of that today as well, because I think this greenhouse that we looked at today, the greenhouses, did not have perimeter insulation. We're going to talk about that. So we need to calculate all these different heat losses, add them all up to try to figure out what that heater or boiler capacity needs to be. There are some special circumstances if your greenhouse is located where we have high wind conditions. Again, thinking about this infiltration situation, when you have a lot of winds, when you go outside yourself and you don't have a lot of clothes on and it's very windy, you're colder than when there's not so much wind. That's the same for a greenhouse. A greenhouse will lose more heat when there's high wind conditions. And so if that's the case for your location, for your greenhouse, we need to make some adjustments. We need to add some additional heat loss as a result of that to our calculations. In addition, if you want to maintain a large temperature difference between your inside, your set point, and the outside conditions, again, because of that large temperature difference, you can lose more heat. Think about your house. If you crank the temperature up real high inside, you keep it nice and warm, but you also lose more heat than when you have a lower temperature inside. And so we need to, again, take that into consideration, add some kind of a factor in our calculation that accounts for that. So then at the end, the total heat loss from the structure is the sum of the three components: the structural heat loss, the infiltration heat loss, and the perimeter heat loss. We take these adjustments into consideration if needed. And then we have a total heat loss for the structure, and then the final step that we have to think about is the fuel conversion efficiency. So depending on the fuel source that you combust, that you burn, each of those combustion processes comes with its own conversion efficiency, and we have to take it into consideration in order to calculate the final capacity of the heating system. So this is in a very shorthand form the steps we have to go through, and I want to next look at some of these calculations that we have to do to come to our final conclusion. So the first step is the structural heat loss, so what we lose through the structure. That is typically mostly the covering material for a greenhouse, but it could also be some structural components. And here you see the equation for that. It's a fairly simple equation. We need to know something about the material involved and how well that material conducts heat. We call that the heat transfer coefficient, or the U value, which, by the way, is the inverse of the R value. So if you go to a box store, the Lowe's or the Home Depot, and you look for insulation material, you'll typically find an R value. Well, the U value that we use for our calculation is nothing more than the inverse of the R value that you are familiar with when you go to the hardware store. We need to know the surface area associated with that particular material, and if we have multiple materials, for example, for a greenhouse that is covered with double poly, as well as some areas that are covered with polycarbonate or another rigid plastic material, we need to, for each of those individual areas, calculate the area involved as well as the associated U value for that material. And then we need to know something about the temperature difference, and we typically use for the inside temperature the nighttime set point temperature, because the nighttime is typically the time of the day where we expect the largest heat loss, because it's the coldest outside. It doesn't have to be that way. It could be a very cold day during the daytime, but typically nighttime is the coldest time. So for the inside temperature, we typically pick the nighttime temperature set point. And then we need to know something about the outside temperature, and the outside temperature, of course, depends on the weather. And so that would vary, and that would make our calculation kind of tedious. And so we do something to make it easier on us. We use a design temperature, a temperature that's recorded for the particular location over many years. But we make some compromises, and I'm going to talk a little bit about that in a second. So once we know these three components of the structural heat loss equation, we can simply multiply them to get our overall heat loss expressed in BTUs per hour. Now we set the inside temperature is typically our nighttime temperature set point. So the U value was something that we can get from materials. Once we know the materials involved for the cladding material and sometimes for the structural components, we can figure out the U value by looking at manufacturer's data or by going to an engineering table. We can calculate the area of the particular structural component involved by looking at the plans, for example, the greenhouse, or by taking measurements. We can figure out what the grower is using for their inside nighttime temperature set point. The only thing we don't know yet is the outdoor temperature. And as I mentioned, we use a sort of compromise. We use something that's called the outdoor design temperature. These are values that are calculated for many locations across the country. In fact, one of the handouts gives you a table for many locations that gives you this 99% design temperature. And what that means is that this particular temperature that we use for our calculations is only exceeded, or it's only lower than that temperature 1% of the time. So when you take temperature readings for particular locations over a long period of time, you can calculate what that particular temperature should be that is only exceeded 1% of the time. We call it our 99% design temperature. And the reason we do that, if we went with the absolute coldest temperature ever recorded for a particular location, we had to design for a very large boiler system, and that capacity would only be used a very limited number of hours over an average year. So we back off a little bit. We say, well, can we live with a little bit smaller heating system that is not as expensive and is perhaps used more efficiently than that very large system that we would need for the very coldest temperatures ever recorded for this particular site. Now you can immediately then ask me the question, well, what do you do when we exceed that value, when it gets actually colder than that 99% design temperature? And the grower has two options really. The grower can bring in standby heating, for example by using kerosene heaters or another fuel source that you can use. But you have to have those pieces of equipment available. But what most growers do, they will just back off their inside set point temperature. They say, okay, I can live with a certain number of hours when my temperature is actually a few degrees below my nighttime set point temperature. And as long as those number of hours is limited, and as long as the temperature drop is not very significant, that is an acceptable way to go. So growers typically say, okay, I know I can't have a boiler system that is providing the heat for the absolute coldest conditions. I back off a little bit, I go with the 99% design temperature, and for those extra hours that the temperature exceeded, for example, where I lived last week, we had that situation occur. We were going down to 5 or so. The design temperature for my location is around 7 or 8. So we went below that temperature. That meant that if you went with the particular calculation I'm talking about, you would have to lower your inside set point temperature a little bit to still have to still use the capacity that the boiler is able to provide. So you see, for different locations around the country, including Richmond, for Virginia, that I could find data for what the design temperatures are going to be. So you get some idea of how those temperatures fluctuate depending on different locations around the country. And I also included this chart that shows you, in general, what those temperatures will be depending on your location. And you also have in your handout that more extensive chart for many more cities around the country. So keep in mind that this approach is a compromise, that there are a certain number of hours on average during the year that your boiler or heating system will not be able to maintain your set point temperature, but that's a compromise we feel is acceptable. The next thing that I already alluded to, we have to know are the U values. And I said you can go to engineering tables or you can go to manufacturer's data. Here, in this table you have some information about the most common values for the most common materials that we use for greenhouse covering materials. Single or double glass, single or double polyethylene film, the double layer, sometimes triple layer, of rigid plastic panels, acrylic or polycarbonate, the values. You can also see what happens when you add an energy curtain. The value is dropping significantly, so I want to re-emphasize, I'm going to come back to this later, that adding an energy curtain is typically a very smart decision for a grower. And I also included in this table some other common building materials just to get you an idea how that U value compared to these other common structural components. So the thing to remember here is that if you double the layer, whether it's glass or polyethylene film, you see the number in parentheses drop significantly, and the lower heat U value means less heat loss to the outside, so it's a better situation. And then you can also see what happens when you add the energy curve. You have another significant drop in the U value. So we've dealt with the structural heat loss. The next thing we need to worry about is the infiltration heat loss. So air movement through unintended cracks and openings in the structure by which we can lose heat. We need to follow, and again, a pretty simple equation that includes the greenhouse volume. So we have to do some calculations or use the design of the greenhouse, the plans for the greenhouse to come up with a number. And we need to look in the table that you see in the bottom of the slide here to figure out what, on average, this number of air exchanges is that is occurring as a result of this unintended infiltration. And you can see here that depending on the glazing material you use, and depending on whether this greenhouse structure is in good condition or in poor condition, you can find some numbers here that you can then plug into the equation at the top to figure out what the infiltration heat loss is going to be. And I point out here that when you do the design approach, it's typically a good idea to follow a conservative method, and that means that you have to take a larger value for this number of air exchanges that is occurring as a result of this infiltration through unintended openings, and therefore you will get a little bit larger heat loss that then helps you design hopefully a more robust system. I mentioned this to a few of you, but we looked at some of the fans in the greenhouse today, and typically we have a situation like you see in the upper right-hand corner where we have louvers on the inside. We always want the louvers on the inside because that has that increases the efficiency of the air flow through the entire system. The fan blades give a twist on the air as they are pulling the air out of the greenhouse. And if that twisting air would hit the louvers on the outside, that would reduce the efficiency. So we typically put the louvers on the inside to not have that happen, to have maximum efficiency. But as you all know, these louvers are typically made out of aluminum or fairly flimsy sheet metal, and over time they don't close very well anymore. They get dent and they have little openings. So again, think about the infiltration heat loss that's occurring. So a more recent design is this roll up or roll down kind of louver system, where there's a curtain material that as soon as the fan is turned off and no ventilation is needed anymore, this will slide down much like an overhead garage door, but it's closing off very carefully the entire opening that is left by the fan housing. So it's a method of reducing this heat loss by infiltration or exfiltration, depending on which way the air is moving. So this might be an upgrade that growers could, if they are concerned about this particular heat loss issue. The next thing we need to worry about is the perimeter heat loss, and again we have a fairly simple equation. We need to know something about the perimeter itself in order to determine this perimeter heat loss factor. There's a small table here that tells you the numbers to use, whether that perimeter was insulated or not insulated, and I'm going to show you a picture next what I mean with that. And you need to know the greenhouse perimeter. Again, that's something you can measure or you can find from a engineering drawing of the structure itself. One of the questions that people sometimes ask me is, well, if you are concerned about the perimeter heat loss, what about the heat loss to the soil underneath the greenhouse floor? And we've done some research on that, and we pretty much convinced ourselves that if you are located on a site where you have a relatively high groundwater table, which typically means that the soil is relatively wet underneath the greenhouse floor, then you have an opportunity for a lot of heat conduction, because water is a very good conductor of heat. So in situations where the soil underneath the greenhouse is relatively wet, you could lose significant amounts of heat to the soil underneath the greenhouse floor. And in that case, it makes sense to also think about an entire horizontal layer of insulation underneath your floor. But if you are located, for example, on a hillside where you don't worry too much about groundwater, the groundwater table is very low at your side, and you have a well-draining soil, so that your soil underneath the floor is dry, then that soil will not conduct heat very easily. And I think that you don't have to worry too much about adding an extra horizontal layer of insulation underneath your floor. So here's what I'm talking about, what I'm telling you about perimeter insulation. You see two examples, one of a greenhouse construction in progress, where the knee wall or the curtain wall on the side, so the first 3 or 4 feet or so, are made of insulated material that is not transparent for light, but it's actually extended a foot or sometimes 2 feet down into the soil to try to block any heat that is accumulating on the inside, and particularly on the floor or in the soil on the inside of the greenhouse, from easily escaping to the outside. In the wintertime, the outside soil, of course, is exposed to the outside conditions and could get very cold. So there could be a very easy conduit for heat to be converted from the inside to the outside, or transported from the inside to the outside. So by putting this vertical barrier, if you will, we can prevent some of the heat loss, and we reduce the perimeter heat loss of the structure. The picture on the right, on the bottom, showed you that exact same idea. In this case, it was done for a hen house area or a work area. But again, we put about 2 feet or so of rigid insulation board straight down to try to create this barrier that would prevent some of the heat from escaping from the inside floor to the outside soil directly adjacent to the structure. So I give you some recommendations here. You want to go at least a foot deep, preferably 2. You want to have as thick an insulation material as you can afford. Particularly in colder locations, so in the northern parts of the country and in Canada, you want to use the larger depths and the thicker materials. If you install this, you sometimes run into issues with the footing that is used for the posts, because that typically is made out of a concrete base, and that extends right in the space where you want to put this vertical insulation material. So sometimes you have to work around that concrete footer and try to close any gaps as best as you can to try to make maximum use of this idea. Another relatively easy and I thought innovative approach for trying to reduce some of the heat loss from the structure was this grower that I visited in Connecticut a couple of years ago. In the early energy crisis, greenhouses were, of course, hard hit by the high energy crisis. This was in the 70s. And at that time, all kinds of research was going on to try to figure out how we could insulate greenhouses. And what they did at that time was recommend that people, particularly on the north wall, put some solid insulation to try to reduce heat loss. But when they did that, they discovered that as a result also a significant amount of light was blocked off. Think about cloudy weather like today, where light is mostly diffused, coming from multiple directions, not just from the south or from the direction of the sun, but also from the north side, because of all the bouncing around of light in the atmosphere in the clouds before it reaches the surface. It is important to also have light coming through your north wall. And so this grower married these two ideas and said, okay, I want to insulate my north wall, but I also want to make sure I get enough light in. So they used bubble wrap material to insulate the north-facing wall of the greenhouse to try to reduce heat loss. I thought it was an interesting idea. Okay, I mentioned that under some conditions we have to make adjustments for when we have a high wind condition or when we have a large temperature difference between the inside and the outside of the greenhouse. This slide is trying to tell you how we do that. So if your temperature difference is larger than 70 degrees, so the difference between your inside set point and this 99% design temperature, and if your average wind speed exceeds 15 miles per hour, you need to make these adjustments. So this average wind speed is something you may be able to get by contacting the local weather station, or again by looking at an engineering table for a particular site that tells you what the average wind speed for that location will be. And then it's probably easiest to go directly to the example. So we have an example here where the temperature difference is actually 80 degrees. So it's 70 was the cutoff, so it's higher than that. And it tells you here that for every 5 degrees above this 70, we need to add a factor of 0.08. So we are actually 10 degrees above 70 when we have a temperature difference of 80. So the factor becomes 1.16. It's a multiplication factor. And the same for this example where we had a wind velocity that is 25 miles per hour. It tells you here that for every 5 miles per hour over 15 miles per hour, we have to have another conversion factor, another component here. So that adds up 25 miles per hour. It's 10 miles over the limit, so you have to do twice the factor. So you end up with a number of 1.08. And if you add them together, you get a factor of 1.24. So this is the multiplication factor that you have to use for your overall heat loss calculation to accommodate the situation of a very large temperature difference as well as a high wind condition. So you do all the calculation that I showed you before, then you figure out this multiplication factor, you multiply your answer with that multiplication factor, you get a bigger number that you then use for figuring out your oil capacity, or your heater capacity.
Quick question on that. Does that assume that the greenhouse is sealed up well?
Yes.
Okay.
Yeah. Yeah. So the next thing that I mentioned that we need to worry about is the fuel conversion efficiency. And this table that I took from the U.S. Energy Information Administration website. And you have to remember that this is data for last summer. Oil prices, of course, have significantly changed since last summer. But they have information about different fuel sources, what the unit prices average for the entire country are, what your BTU, the energy capacity per unit, so the unit is kilowatt hours or gallons, depending on the fuel source. And then it calculates what the dollar price is per million BTUs. Now we're trying to compare apples to apples here by converting the different fuel sources to an energy component and then associating a dollar value with the energy component. But to be really making a true apples to apples comparison, we have to incorporate the conversion efficiency. You see that in the last one with the last column here. These numbers show you how much energy you can get out of converting a particular fuel source to a heat unit. And the heat unit we use is a million BTUs. So you can see that for electricity, that conversion efficiency is very high. If you use electricity for heating, then pretty much all the energy, electric energy that you provide is converted into heat energy. There's very little loss. So from that point of view, using electricity is a very good thing to do. But of course, electricity is a very expensive way of heating a structure. So this conversion efficiency is really an important number that you need to keep in consideration when you want to know exactly how much energy you can get out of a particular heating system using a particular fuel source. And then the last column here is incorporating this conversion efficiency. So this is a really apples-to-apples comparison where you can see how the different fuel sources compare in terms of the amount of money you need to spend for getting a million BTU of heat energy out of that particular fuel source. And so I highlighted the cheaper ones, the cheapest one being coal. And although there's other reasons for why we don't want to use coal, when you look strictly at a monetary consideration, then it looks like coal is still the best fuel source to use. Natural gas is not far behind and followed by wood based on this data. And of course, as I mentioned already again, oil prices were based on June data for last year. Right now, oil prices is about half of what it was in June, so that picture has changed, but nevertheless, oil is still more expensive than any of the three energy sources that I've highlighted here. So if you really want to start comparing fuel sources, you have to go through a calculation like this. You have to look at what the units are, how much energy is contained in those units, and you have to include the conversion efficiency. Now, some of you may pick a bone with me and say, well, my gas heater is a lot more efficient than 82%, and that's fine. You can use your own conversion efficiency numbers for your own system. That 82% I think is a reasonable number for an average gas-fired heating system. So depending on your own numbers and your own prices, you can do the same kind of calculation to figure out for your situation what these numbers will be. So next I wanted to review some different heating systems. We've seen unit heaters, so I think you all know what they are, what they look like, how they work. It's basically a heat exchanger with a fan, and we provide fuel. It could be gas, could be oil, it could be something else that is combusted inside, and then we blow warm air or air through the unit, and the heat exchanger exchanges the combustion heat with the air that we blow through the system. Sometimes we are concerned about byproducts that are formed through the combustion process, and in that case we have what we call separated combustion systems, where we bring in outside air for the combustion process and we remove any combusted air or combustion products through a different stack system to the outside, so that the inside air is never mixed with the combustion process. There's no release of any combustion gases inside the greenhouse. Sometimes we do want combustion processes inside the greenhouse when we want to release CO2 in the greenhouse for added photosynthesis, added growth. We also have these type of furnaces, but just like unit heaters, furnaces have particularly a challenge in distributing that air uniformly throughout the structure. Think about these units in operation. It's basically a large fan capturing heat from the heat exchanger and then blowing a large jet of warm air into the greenhouse. And it takes some time for that warm air to mix with the greenhouse air and distribute evenly to then heat the crops. So one way of trying to deal with that is to use a polytube system. It's an inflatable polyethylene tube that we attach to the end of a unit heater, or sometimes we have an extra blower in between that inflates the tube. And the idea is that we blow the warm air that is generated by the heating system through this inflation tube, and then all along the length of the tube we have little openings through which that air can escape. And if we design the system properly, that air escapes with a fairly high velocity, and as a result that momentum is carried over, that momentum results in proper mixing of that warm air that comes out of those little openings with the greenhouse air for a much more uniform distribution of that warm air, compared to just letting these unit heaters blow their warm jets of air into the structure.
So it's simply like smaller holes at the front end, larger holes at the back end?
Yeah, that's the proper way of doing it. Very often you see the same size holes all along the length of the tube, but if you want to do it properly, you start with larger holes, and the other way around, you start with smaller holes and go with larger towards the end to try to make the amount of air and the velocity that comes out with the same all along the length of that tube. Yes.
Does the tube come as a retrofit product so that it can fit on any of those? Or?
The tube comes for specific diameters. It could be 18 inches, 20 inches, 24 inches, something like that. So you need to know what you're going to attach it to. But other than that, it's a simple tube. It comes in a flat roll, and you just unroll it and you hook it up, and it's done. It's very simple. Yes.
Is there any studies on savings as a result of having it more evenly distributed?
Savings in terms of even distributed air, I don't think so. I don't think we have seen studies like that. But it's the quality that we can measure, right? It's the quality of the plant material. So if you see unevenness, and a grower will see that when they start to market their product, and you know that you can use this system to try to reduce that unevenness, then I think they've made some gains. But I don't think we have hard data to say, okay, you've saved X number of percent by using this tube system.
Okay.
It's more an issue of quality and uniformity as anything else. As I alluded to, we have different types of unit heaters. This is a listing of the most common types. We have units that we call gravity vented, which are buoyancy vented systems. We make use of the fact that warm air is less dense and rises, so we make use of that natural process to try to draw the exhaust gases out of the structure. We have power vented unit heaters that use a small fan to try to draw air out of the combustion chamber and to the outside of the greenhouse, to try to make sure that that process is done properly and we don't end up with combustion gases inside the structure. We have, as I already mentioned, separated combustion units where the intake as well as the exhaust from the combustion process are completely separated and are challenged through a different duct system so that we don't have any air mixing between the inside and the combustion gases for the process. We can have something that we call condensing systems, and I'm going to come back to this later. If you do a combustion process and you do it well, then you should end up with only carbon dioxide and water vapor as the end products. But if you think about it, in order to get water vapor, we have to expend energy. The heat that is generated in the combustion process, some of that heat is used to make water vapor. And if we condense that water vapor back down, we can extract some of that energy again and increase the overall efficiency of our process. We call it the condensing boiler system or heating system. And as I said, I'm going to come back to that later to show you a little bit more in detail how that works. But the idea is that we can convert that water vapor that was formed during the combustion process. We can condense that water vapor, make water out of it, and capture some of that heat that was contained in that initial process of forming the water vapor. And then we have a system, as I mentioned, we call it a direct fired unit heaters, where we are trying to use, hopefully when the system is properly adjusted and properly functioning, we try to make use of the carbon dioxide that is formed in the combustion process to increase the photosynthesis, because carbon dioxide is of course used by plants for the process of photosynthesis to grow and develop. So we are explicitly in this case trying to get extra CO2 inside the house, so we want the combustion gases to be released inside the house to increase the CO2 concentration to boost plant production. But we have to be concerned then that the system is properly adjusted so we don't get any potential harmful byproducts of the combustion process released into the house. For example, ethylene and carbon monoxide ethylene particularly for plants and carbon monoxide obviously for people can be an issue, as well as the water vapor. If you produce too much water vapor, we can increase the humidity inside the house and it can have all kinds of disease issues for plant material. So that's also a concern. So this is possible, but you have to know what you're doing. You have to have properly adjusted equipment that can make sure that none of these harmful byproducts are actually being released inside the house. Here's some examples of a hot water system. We saw some of these components today. We typically have a boiler. This was a gas-fired boiler with a large plumbing system with lots of pumps and mixing valves. Typically, one system is is providing hot water to multiple zones or regions in the greenhouse that can be operated at different settings. And here you see some of the pipes, in this case along the perimeter. There's typically also pipes overhead. We can have different types of pipe. These are thin pipes, these are smooth pipes. We can also put pipes on the floor. You've seen pipes today that were installed in benches, but all of these systems use water to move energy, heat energy from the boiler system to the ultimate greenhouse location where it's needed.
Okay, what's your diameter of that thin pipe right there?
This is probably 1.5 inches, maybe an inch, 1.5 inches, something like that. Of the pipe, that's what you're talking about?
Yeah, so that's under bench?
This is under bench or around the perimeter. The number of fins typically tells you what it's used for. When we look at the greenhouse today, we saw only 2 fins, so it's less convective radiation coming up, convective energy coming from the system. These were used for perimeter and overhead heating, so you want more energy coming out of that system, so you have more fins. Yeah. Yes.
Does the recommendation for the the insulation in the floor change if you're using the in-floor heating?
No.
Please repeat that question.
So the question is, if we use in-floor heating or hydronic heating, do we still need to, or should we install insulation underneath the floor? And I think the same answer would apply as I gave before. If you are in a wet location, you would probably want to think about it. In a dry location, I would say no, because dry soil underneath your floor will be a poor conductor for heat.
So how do you insulate the floor? What do you use?
You would use probably a rigid insulation panel, much like you see used in residential and commercial construction. Could be 1 inch, could be 1.5 inches or 2 inch. And it depends on the cost, what thickness you want to use. That's typically the motivation.
And then you pour the concrete on top of that?
Correct, yeah. And if you have a floor heating system, you typically attach your heating pipes to your reinforcing wire that you put in place just prior to pouring the concrete. An array of different heating designs are used both for hot water and for hot air. You can see several of them here. We have overhead and perimeter heat. We have bench heating. We have inter-canopy heating. Pipes that are placed between rows of plants is typically something you see in tomato or cucumber or pepper houses, where the pipes are not only used for heating but also as a rail system for small carts that we can use to drive between the rows of plants. We have floor heating, could be directly inside in the soil, it could be in a concrete floor, could be a mix of different heating systems. We have perimeter heating that is using fans to distribute that air. We have these overhead unit heaters. They could be horizontal, could be vertical, as in this case. We talked about the poly tubes, and the poly tubes could be overhead as well as underneath the benches or on the floor. So a variety of different designs are used, depending on the crops that you're growing and depending on, typically on grower preferences. One of the questions that growers often ask me, well, if I had a choice, what would I recommend? And if I had a choice, then I would typically opt for hot water systems, particularly when I was concerned about uniformity. I think it was mentioned today, as well as I alluded to it earlier. Hot water systems provide a much better means of distributing that heat more uniformly compared to hot air systems. And so for crops where uniformity is really key, for example, growing seedlings that are only in the greenhouse for a very short amount of time, that you want to grow at the same rate because you want to harvest them at the same time, uniformity is important, so then a hot water system is the way to go. But hot water systems are more expensive than air systems, and that is typically a major concern for many growers. So I do have a lot of growers who have hot air systems because they are concerned about the cost of those hot water systems. And if you do have a hot water system, you should not forget about the fact that you need water treatment. Often we use dissimilar metals in hot water systems. We have perhaps aluminum, we have steel, we may have copper or brass for various components of the system, for mixing valves, for pumps, as well as the regular pipes that we use. And if you have that situation, then you typically have the galvanic effect that creates corrosion in your system. And one way of trying to combat that is to have a good water treatment system. So you have to have some chemicals, and it has to be checked regularly. Typically you contract out with a specialist that does that work for you, but you have to keep an eye on the composition of your water inside your heating system to prevent premature failure due to corrosion. Then I wanted to spend a few minutes talking specifically about root zone heating systems. If you are really concerned about heating and uniformity, I think root zone heating systems are really the way to go. They provide you with the highest uniformity, but they have some limitations too. They provide only a certain amount of heat, because if we wanted them to provide all the heat needed to maintain the temperature in the greenhouse, we had to crank the temperature up really high. And typically with these root zone systems, the crop is really close. We set the crops directly on the floor that's heated, or we set the crops on top of a bench that's heated. So we can't crank the temperature up very high in a root zone heating system. So we can provide some heat, but we have to have additional capacity to provide more heat for the colder conditions throughout the year. So it's not a single heating system. You need to have a root zone heating system plus additional perimeter, overhead, or whatever else you need to install to make up for the additional heat requirement. Another point I think that is important to remember when you have a root zone heating system, so that typically means you grow the crop very close to your heat source. That means that very often growers are able to lower their air temperature. And as you remember, hopefully from what I said earlier, when you lower your air temperature, when you lower your set point temperature, you have less heat loss in the structure. So you have less expense on maintaining the temperature in the structure. Now, there's a caveat there, because if you lower your air temperature, that may still have an effect on your crop. So you want to play this game a little carefully. You want to probably experiment with this first before you go full out. Because if you lower your air temperature, you may reduce some of the metabolic processes in the plants that reduce plant growth. So you want to investigate this carefully before you start lowering your air temperature. But many growers report that when they have root zone heating systems that provide that heat energy, a lot of the heat energy close to where the crop is growing, they have been able to lower their air temperature, and as a result, they have been able to reduce energy consumption. Now, one subset of the root zone heating system is the floor heating system, and floor heating systems have an added benefit that in case of equipment failure, so it could be a power loss, it could be a pump failure, it could be a boiler is down, that slab of concrete or the slab of floor that was heated contains a fair amount of heat in it. And that can buy you some time, maybe not enough, but perhaps a few hours, before you get into dangerous temperature conditions in your entire greenhouse operation. So it can buy you some time when you have a catastrophic failure. And as I mentioned, you need some additional heating capacity because we can't crank up the heat very high in root zone heating systems because the crop is so close. So some examples you've seen today. This is another modification on that. This is the tubes are directly laid on top of the expanded metal that forms the bench, and then the trays are placed directly on top of the tubes, and you see here the manifold system with the pump that circulates the warm water through the system. You can also see the rolling benches here, and underneath the benches, these white pipes are the heating pipes that provide hot water, so heating energy to the crop. You can see also the distance here. This pipe is probably carrying a little bit higher water temperature, so it's placed some distance away from the bottom of the table so that we don't get into the situation that the root system is heated too much. Here you see an example of a floor heating system where we don't have a concrete floor, but just a regular dirt floor, or hopefully a sandy floor, covered with a landscape fabric. You can see the tubes, the water carrying tubes going directly into the ground. They form loops, so a supply pipe and a return pipe, so one loop is going all the way to the end of the greenhouse, coming back, and then is attached to the return line, and then goes back to the heating system. Fairly simple installation, no concrete floor, just a dirt floor with a landscape fabric. And what you need to do in order for the system to transport that heat that is being released into the floor to the crop is you need to keep this relatively moist. So keeping it a relatively wet environment, that's where the landscape fabric helps to keep that layer in which the heating pipes are embedded relatively moist, because that moist soil is a good conductor for heat. And as I mentioned, you can also install a heating system directly in a concrete floor. This is a situation where we have a heated floor that is also the irrigation system. So this is a solid concrete slab with heating pipes embedded in it, and then we designed, before we poured this concrete floor, this is a research greenhouse, we designed the system so that there's a plumbing system underneath the concrete that we laid out carefully before we poured the concrete, and after the concrete was poured, we drilled holes directly through the concrete into our plastic pipe plumbing system that is then connected to an underground storage tank where we maintain our nutrient solution, and then we can pump for an irrigation cycle. We can pump the water up to the floor. The plants are sitting directly on the floor. You see here a rubber bumper around the crop to maintain the nutrient solution in the growing area. And then at the end of the cycle, that lasts a few minutes, the pump is shut off, and all the water, because of the shape of the floor that is sloped so that it drains well, all the water drains back into the underground tank for the next irrigation cycle.
So that's basically just a big ebb and flow floor. The whole thing's like a big hydro table.
Yes, exactly. Yeah.
So what about salt buildups and those kind of things on the floor of the? I mean, do you have to assume you just clean that out after every use or every crop, or what's the? Yeah,
the question is about salt buildups. So nutrients in the solution that could potentially build up. If you design the floor properly and you drain any excess irrigation water quickly back to the holding tank, you have very little standing water on the floor after the irrigation cycle, and thus very little opportunity for salts to accumulate. Okay. And so I've never seen that as an issue. And if you do finish your crop, then typically, yes, you would clean your floor, you would sweep it, and you may wet it if you wanted to, and then clean out your tank and then start all over again for the next crop.
Okay. And so your collection tank is underneath, or your reservoir, if you will, is underneath all that slab?
Yes. Yep.
Is there a manhole to get down in?
Yep, exactly. Yep. We used a large septic system tank, a concrete tank that was just delivered. We just dug it into the ground. It has covers, manhole covers to get in, and we hooked it up to our plumbing system and installed the pump, and that was it. So it takes time to install it, and it takes some thinking to properly lay it out, and especially to mark carefully where you lay your plumbing system, because you have to drill through the concrete. You can't see anymore where the pipe is. You have to remember where the pipe is. And then you drill holes, and if you did it well, you hit the pipe, and then you're in business. We talked about these IR, infrared heating systems, or radiant heating systems. I think they are not so useful for greenhouse applications. There's others that think differently about that. We talked about the fact that the line of sight, or the point of heating, has to be in view of the radiator. So particularly for crops that have multiple layers of leaves, lower layers of the canopy will not see much of that heat radiation, and so therefore you get uneven heating within a plant canopy. But it allows for, and this was alluded to already today, it allows for lower air temperatures. Again, this can be an energy saving issue. After heat is absorbed, for example, by your skin or by the surface of a plant, it is typically dissipated by radiation and convection. So there is some movement of that heat, but that takes these other processes that are typically not as efficient as the direct line of sight radiation emitted by these systems. Also, in lower greenhouse ranges, so in the older parts of the greenhouse operation that we saw today, where the greenhouse gutter height was relatively low, you have a challenge of mounting these systems high enough so that they can cover a large enough of an area, because there's just not enough room in the greenhouse structure to put them a certain distance away from the plants. And so in older greenhouses, this is a challenge for mounting these systems and cover larger areas of the operation. But the response time is very quick. You turn them on and the radiation starts instantaneously, and as a result you have instantaneous heating, which can be a benefit.
Could you mount that under, like a system like that under a bench, or a very low level system for like roof heating, or is that not practical?
Yeah, the question is, could you mount these radiant heating systems underneath the bench? I assume you can, and it might work. One of the challenges I see is stuff falling on it, particularly water, and that probably creates all kinds of issues. So I don't think it's a very practical idea, but it's, theoretically I think it would work. Other heating systems, we talked a little about wood today, but there's other biomass sources. We've seen growers use corn and switchgrass. Miscanthus was mentioned today, and maybe other grasses that we could use. Some growers, depending on their locations and the geology of the site, can make use of geothermal sources. So hot water sources, typically a result of volcanic activity or geological formations deep underground. I'm talking now about miles underground, typically. We can also make use of ground source heat systems. Typically we use heat pumps, which are systems that are very similar to a refrigerator, except you can run them in opposite direction. You can run the refrigerant in opposite direction. That means that in addition to cooling space, you can also use that same system to heat something, just by reversing the flow of the refrigerant inside of it. And so if we installed a loop underground, and typically this is installed in shallow depths, we have a large plumbing system, a large tube, a large loop of pipe underground. We can run water through it or a refrigerant through it. And we could then dump heat energy in the summertime that we collect in the greenhouse when it gets really warm in the greenhouse, and therefore cool the greenhouse. And in the wintertime, we can extract heat energy from the soil at a certain depth. The soil temperature is pretty much stable year round. If you go 3, 4, 5 feet deep, the temperature is probably 55 Fahrenheit or so, pretty much year round. So in the wintertime, that 55 degrees several feet underground is much higher than the outdoor temperature, so we can extract heat from that soil and then dump that heat inside the greenhouse. So these ground source heat systems, these heat pump systems, could be very effective for heating greenhouses, particularly if you match them with a storage system. If you could run these heat pump systems at their highest efficiency, that means you have to run them at a certain rate, even though you may not need all the energy at the moment. But if you could store excess energy in the form of hot water or maybe cold water, depending on what season you're running it at, then you could increase your overall system efficiency and make much better use of these systems. And I think there's potential there. Not too many growers are using them, but I think if energy prices continue to be high, we don't know what's going to happen with the oil prices, but I suspect we will see a return to higher prices. More growers may want to look into this. There are also opportunities for, and this was mentioned today already, for greenhouses located near waste heat sites, so it could be power plants, could be other industrial processes, and I'll show you a picture of one of them in Pennsylvania that has done this successfully. And then, it was mentioned today earlier, I think there's really good potential here for combined heat and power. I have an example of using a microturbine, but you can also use regular reciprocating engines to try to use combined heat and power, because that, I think, creates much higher overall system efficiencies than having a boiler system or a heating system on site, as well as extracting electric energy from the grid. So combined heat and power systems are systems that, another word for it is cogeneration. What they do is they generate both electricity and you capture the waste heat from the process. So you generate both electricity as well as heat from a single system, as opposed to the traditional situation where you have your boiler system that generates your heat energy and you extract electric energy from the power grid. And then I want to talk a little bit more about this, because I think this is also a very promising technology, condensing boilers. So I'll get back to that in a minute. So this is a system that I think we heard mentioned today. It would be slightly different than what's happening now with the large logs that are being used. You would have a shredded wood waste source, so you'd have to run the logs through a shredder to make a perhaps a little bit easier, manageable, and easier to handle type of material. You would have a conveyor system. You bring it inside the building. You have this walking floor system that allows for large storage volume to be ready to be combusted. It makes the management of the system a little easier. And then at the end of this walking floor would be another conveyor belt that then brings it to a biomass boiler, in this case a boiler that generated hot water, and then that hot water could be used for immediate needs, or as in this case, it could also be stored in an insulated water tank for later use where the greenhouse needed more heating. So the trick with these systems is, and this is why this storage component becomes so critical, is that you want to run these units at their maximum efficiency as much as possible. If you need a little bit of heat, in the old approach, you would have to start up this large boiler system and produce that little bit of heat, and then you would shut the boiler down again until you had the next request for heat. But if you could run your boiler at its maximum efficiency, let's say that's 80%, so you produced way more energy than you needed because you only need a little bit of heat, but you could store that excess in this insulated storage tank in the form of hot water, then you maximize the efficiency of this system. So you always try to operate it as much as possible at the maximum efficiency to try to make the best use of your resources. In New Jersey, we have a grower who is using wood pellets, so it's the same idea. Sawdust, in this case, is formed into pellets that are shipped on site by tractor trailers and then stored in these large silos and then augered in with a simple auger system into the boiler system. So yes, it's an extra step. You have to process your wood and make these pellets, but once you have these pellets, it becomes a fairly easy, manageable system. And once you figure out how to work with these silos and get past some of the challenges of running an auger system, it's a very easy way of getting your fuel source to your boiler system. So here you see the inside of the boiler room where he installed a pretty large, it's about a 7-acre range in northern New Jersey, running this pelleted wood into this boiler system. And otherwise it's a fairly similar, it's a combustion chamber with a lot of pipes around where you pump your water through. So here's where the pellets come in into this hopper, and then the hopper, based on a computer control system, introduces pellets into the combustion chamber. So if a lot of heat is needed, a lot of pellets are pushed in. If little heat is needed, only a small amount of of pellets is pushed in. The only challenge for us in New Jersey is that we are one of the states that is not in compliance with the Clean Air Act, and that means that our Department of Environmental Protection is very keen on limiting additional, particularly particulate matter emitters in our state. And so when our grower switched from, in this case he was using fuel oil, that was one of his reasons why he wanted to go with a different fuel source. He switched from fuel oil to a wood source. The DEP was all over him because they were concerned about additional particulate emissions because of the fact that we are not in compliance with the Clean Air Act. And so we had to install a fairly elaborate system with cyclone technology to try to capture all the particulate matter before any of the exhaust gases were released to the outside. So there were additional costs in our case involved with this particular heating system. But you don't have to go very big. You can also use very simple, small wood stoves. So it's the same idea. Wood is being introduced in the combustion chamber, the door closes, there's a whole bunch of water pipes all around in the wall of the unit around the combustion chamber. We regulate the rate of combustion by closing down the air supply, so we regulate the amount of oxygen available for the combustion process. So that is all connected then to the temperature sensor in the greenhouse. And then you can see a little pipe here, you run your hot water into your greenhouse and you can use a heat exchanger as we've seen today to get hot air that we can then blow around the greenhouse to heat the greenhouse. Now, you've heard today that it is a bit of a challenge sometimes to keep a system like this stacked. This was a small system that was hand-filled, so potentially you'd have to get up in the middle of the night when it's cold to restack a system like this, as I think is the case at the greenhouse operation we saw today. There are larger systems that allow entire pallets to be driven in with a forklift driven into the entire combustion chamber. And so what growers with larger systems can do, they can pre-stack wood on pallets, and then all they have to do is get a forklift, open the door and drive another pallet into the combustion chamber and close the door and they're done. So there are ways of trying to reduce the amount of labor and the effort that you have to do to keep these systems going. I mentioned ground source heat pumps. This is an example of an installation for a residential home, but it's the very same type of systems you can use for greenhouses. So there's typically two ways to implement this. You can have a horizontal layout where you have a larger area that is needed for running a bunch of loops, or if you don't have space, you can go vertical, and you probably have to have a company that drills wells, so you can install these vertical loops. But it basically works the same way. In the summertime, you can cool down your space by extracting heat energy and bringing it to the soil. And in the wintertime, when the soil temperature is typically warmer than the outside temperature, you can extract energy from the soil and bring it into the space you want to heat. In this case, you can see that there's additional heating capacity needed or perhaps required in case the system itself is not able to provide everything that's needed. And of course, you have an additional water heater here that helps you in case you don't get enough capacity out of the system. For example, for floor heating or for other water heating purposes. Now, if you look at the price here per million BTU, and you remember the table that I showed you earlier, then you see that these ground source heat systems can be relatively competitive with other technologies that we have. So it is certainly something from an engineering and from an economic point of view, a system that I think could be very competitive for heating greenhouse systems. You do, of course, have to install these areas with an extensive plumbing system, and that could be potentially an issue for some greenhouse operations.
On a closed system, loop like that, the $10.37 per million BTUs, where is that? Is that from actually moving the material or pumping of it around within the system?
Yes, So that's the energy that you have to run the system.
Okay.
Yeah. That does not include the components that you have to buy to install the system.
Very similar to what you were saying, using fuel,
Yeah.
basically.
Yeah. I mentioned the case of a greenhouse operation that used waste heat. Here's a large power plant in the background, this greenhouse in Pennsylvania. And I think it was a tax break issue, perhaps an environmental issue as well, where the greenhouse operation was able to come to an agreement with the power company to use some of the cooling water that otherwise would be run through their cooling tower before it was being cooled down, to run that water, a portion of that water, to the greenhouse operation and use heat exchangers in the greenhouse to make use of that heat. So theoretically, this is a very nice system. After you install the plumbing and you install the heat exchanger in the greenhouse, your heat source is basically for free. But I think there is one significant caveat in this system, is that power plants need maintenance. And so they are typically down maybe a month every year. And it's not always in the summertime. It could be in the wintertime that they're down for maintenance. And so you have to have a backup heating system when you are going this route. You cannot always 100% rely on your outside energy source to be available. So you still need your own heating system to provide enough heat energy. We have in New Jersey, as part of the university research system, a 1 acre greenhouse at a landfill site, about 45 minutes south of where I'm at in New Brunswick, New Jersey. The university made an agreement with the county that the county paid for the greenhouse facility, but the university operates it for a nominal fee. And since we are close to a landfill, and part of that landfill is actually finished, is covered and capped, and they are extracting methane gas out of that portion of the landfill, we are using that methane, that landfill gas, to convert that in this combined heat and power system using a microturbine, which is a jet engine, a stationary jet engine. So it's the same technology as in the jet engine, except it's stationary on the ground. We're using that same technology to generate electricity that we can use on site, primarily for our supplemental lighting system. We have a large supplemental lighting system in this greenhouse that requires lots of energy. And any excess electricity that we generate, we can export to a local power grid. We have a special agreement with the power company. It's not a net metering agreement. It's an agreement that allows us to export whatever we have excess and whenever we have it. So we're generating electricity that we can use on site, or any excess can be exported. And then on the exhaust system from this combustion process, we have a heat exchanger that converts that hot combustion gas, that stack gas or exhaust gas, into hot water through a heat exchanger. And that hot water is then pumped into the heating system, plumbed into the heating system of the greenhouse. So this entire setup is producing electricity as well as hot water to help heat the greenhouse facility.
What's your stack temperature there?
Our stack temperature is in the 600 or so degree range. Yeah, still pretty high. So there's more opportunity to collect more energy out of this system.
So that's after it's through the heat recovery, it's 600 degrees?
Yeah. Landfill gas is not as clean as natural gas. You can imagine people dump all kinds of trash in their waste stream, and it ends up in the landfill. And some of those components can be very harsh on engine parts, particularly hydrogen sulfide and a group of compounds called siloxanes, so silicon-based compounds that are part, I think, of cosmetics and other household products that are generated in the process of the microbial breakdown in landfills. In addition to water vapor. So you get all that in the gas that comes out of the landfill, and all of that could potentially damage your engine components. So you need to try to get rid of them. So we have a sulfur removing system. You see these two large cylinders here. There's a proprietary material inside. I think it's mostly iron filings that interact with hydrogen sulfide, bind it up, take it out of the stream. And then we have a compressor system and a refrigeration system that compresses the gas to the right pressure, and also the refrigeration system takes out the moisture and takes out this group of compounds we call siloxanes. And then the remaining gas is clean enough to be combusted in the microturbine that's inside this large gray box here. And the microturbine is linked to a gearbox, and then linked to the generator that generates electricity. And the system has been running for a few years until we discovered that this group of compounds called siloxanes mixed with water is actually a hazardous waste. So in the past we had just run this to a drain, and somebody came and tested it and found out it was highly flammable, and did some more research and discovered that this is a hazardous waste. And we could not bring it back to the landfill. This was my initial response. Well, it came from the landfill. Why don't we just put it back where it came from? But the rule is, once you concentrate your hazardous waste, you have to deal with it. So if it was not concentrated, we could do that. But since we concentrate things, yeah. So long story short, we're not operating right now because we would have to deal with this hazardous waste. We'd have to collect it. We'd have to find an approved storage and handling procedure, and then we'd have to pay for this proper disposal. So that became a cost issue for us. Typically with university grants, you get money up front. You spend your money on installing things, and then when things go wrong, you have to figure out another way to get the money, and so far we haven't figured out a way to get more money to deal with this hazardous waste issue. But I think the idea of running a system like this, perhaps not on landfill gas, but you could certainly run a similar system on natural gas. You probably didn't have to deal with cleaning the gas and the siloxane issue and the hazardous waste issue. Could still be a very interesting proposition. You could still increase your overall efficiency to make this work. And this little picture is trying to show you in numbers what I'm talking about. So on the top part of the slide you see the typical system where you have a power plant generating electricity and an end user using that electricity. And in the case of a greenhouse, we would have a boiler system that would provide our heat energy. And as you can see here in the red at the far end, on the right hand side, it's less than 50% efficient overall. But if you go with a combined heat and power system, you can see that the overall efficiency of this system, where you have one unit that generates both electricity and you capture the waste heat from the combustion process, you get to much higher system efficiency. So we make much better use of the resources that we have available. So I think combined heat and power is certainly something that growers should look into, particularly growers that are thinking about new installations or scaling up their current systems. One of the growers in California has taken this even a step further. They are using gas turbines, so they don't use landfill gas, but they use natural gas. They generate electricity like we were doing, they capture the waste heat, but they also clean the exhaust gases to the point where they have more or less pure CO2 available to them for enriching the greenhouse environment, for boosting plant production. And then finally, they also condensate some of the water vapor that comes out of the system, and then have a certain amount of water that they can use for irrigation purposes. So they have 4 different components that they extract out of their energy system.
That condensed water has no metals in it or anything after it's been condensed from that fuel?
Correct. As far as I know, it doesn't have any metals in it. No.
Well, I was just wondering, back to that combined heat and power that you had before with those siloxanes in it.
Yeah.
Have y'all tried evaporating that with those 2 refrigeration units?
So the amount is very small. If we run for an entire day, our system, which is 250 kilowatt output, nominal output, would generate 5 or 6 gallons of this waste product. So it's a very small amount that doing anything else with would add significant cost for that small amount of volume that you create. Yeah. So that's probably not economic. Okay, I mentioned this several times. Condensing boilers, condensing heaters can be very, very efficient. And what you're trying to do is you try to recapture the energy that was needed to generate water vapor in the combustion process. By condensing the water vapor back to water, you can extract some of that energy, and typically we use that energy to preheat the return water before it gets back into the boiler to be heated again. So, in order to do that, water is involved, and therefore many times we make boiler components out of stainless steel because we don't want them to rust out prematurely. But if you do that, as I mentioned, you can get to much higher overall efficiencies. Another advantage is that these systems can be low mass, so low physical mass, but also low water mass, which can be very useful for greenhouse operations. They can be operated on demand, so you don't have to have a boiler that is running in standby mode to anticipate a request for heat and then have heat relatively quickly available. These systems can be operated on demand, so you can shut them down when you don't need heat, you can start them when you need heat, and they can almost instantaneously provide that heat. They have a relatively small footprint, which could be important under some conditions. They have relatively low maintenance, and they can be combined with high mass, so traditional boiler systems, whether it's steam boilers or other conventional hot water boiler systems. They can be designed so that they can be sort of the pre-stage to the larger mass boiler system. So there are interesting opportunities here, I think, for these condensing boiler systems. So here's in the schematics how the system works. You have your primary combustion chamber where you run your water loop through. All water is coming out, as in this case, going to the greenhouse. And then prior to that water entering into the combustion chamber, you see an extra heat exchange loop where we run the exhaust gases through so that that heat contained in the exhaust gases is extracted, and as a result we see water vapor being condensed and coming out as water. But we use some of that energy contained in the exhaust gases for this process and then increase the overall efficiency of the system. So in summary, trying to wrap this up, trying to give you some suggestions for, I think, what you need to look for in terms of energy savings for greenhouses. I think the first thing every grower needs to start with is to look at conservation measures. It's always cheaper, I believe, to start with conservation than to think about retrofitting or installing new systems, whether that's an alternative energy system or another new approach. I think looking at conservation first is the way to go. The next thing I would do is look at energy curtains or shade curtains. Typically, these are a single curtain that are used for two different purposes, so hence the energy/shade indications. So we make a compromise. Ideally, we would have two curtains, one that would be specifically designed to be an energy retention curtain, and one curtain that was optimized for shading. But of course, that would mean two curtain system installations, so perhaps double the cost. So in many cases, growers compromise and they say, I'm using one curtain for two different purposes. And even in those cases, it's not inconceivable for growers to save 30% on the energy bill when they install this properly. So the payback time for energy curtain is typically very, very rapid, sometimes within one season. So for growers that are concerned about energy conservation and have exhausted the typical conservation measures that they could use, looking at cracks, trying to insulate properly, trying to lower the air temperatures and things like that, then the next thing they could think about is energy credits. I think this is a very good investment. If you look at the developments, technical developments that have happened over the last decade or so, then you'll notice that the typical efficiencies of systems that we were using 10 years ago has, in many cases, increased significantly comparing them to newer systems that are available today. So, looking at higher efficiency systems is typically a good thing to do. Even if your system is still operating perhaps what you think satisfactory, a newer version of your current system may have a much higher efficiency, and it may be well worth looking into whether it makes sense to try to invest in upgrading. People that use oil, there's a technology called flame retention burners that can significantly reduce energy consumption. It's always a good idea, and not all growers are good at this, but to have a maintenance schedule and perform maintenance timely. The numbers in parentheses here are sort of my estimates of what I think the potential savings are if you do this properly for all these different technologies and approaches. But as I say here, the savings are not additive or non-additive. So it doesn't mean that if you uninstall the curtains, you can add it. Keep that in mind. Okay? We can use computer control and variable speed motors and pumps. I think computer control is very important, and not all growers are there yet, but I think if you want to stay ahead, if you want to understand what your system is doing and you want to understand where you could make gains in terms of energy conservation, having a computer control system can be very useful. We talked about lowering your heating system temperature. Again, I want to emphasize that you should do this only if you understand what's going on with your crop and make sure that it doesn't have any negative effects on the crop. Where and if you do insulate, always use the highest R value that you can find for the material. So perhaps it is better to spend a little bit more money on a little thicker layer of insulation because it will pay off in the long run. And for new installations, I think, as I tried to explain, considering combined heat and power or cogeneration systems is a very smart approach.
Doctor, with cogen, real quick, as we were discussing when we were looking at the boiler, the propane boiler over there, isn't it the timing though with greenhouses? I mean, the time you need your heat is typically not when you need all of your electricity. So are you saying use your generation on on-peak times to generate power then? Or, you know what I mean? I mean, where's the balance of the system?
So the question is, how do you balance combined heat and power systems when you produce electricity and heat at the same time, but you may not need them at the same time in your operation? And that's a very good question. I think it requires a management strategy. So it requires you to understand what your system is capable of, what your needs are, and perhaps, as I alluded to earlier, you may have to incorporate a storage system where you can store some energy in the form of hot water over a period of time that allows you to better manage your system to reach those higher efficiencies that are possible. So it is not something that you just install and push a button and walk away from. It's something that you need to manage. You need to understand what's going on, and there are programs available and there are specialists available that know more the ins and outs of these systems that you probably want to consult with to really understand how you can optimize the use of your system. And then I thought my story was not complete, but I shouldn't talk about this too much because you'll hear a lot about this tomorrow. There is an interesting and a useful tool available called Virtual Grower that allows you to do some of these calculations, and particularly allows you, which I think is one of the main values of this software program, allows you to start asking yourself questions. What happens if I install an energy curtain? What happens if I install a higher insulation value, or use a different fuel source, or use a different covering material? What is the impact of that change on the bottom line for my operation? But you'll hear more about that tomorrow. Some useful references, you can look through this. I think all of these are interesting, and if you have difficulty locating them, let me know, and I'll be happy to try to help you get to these. Some of them, I think, are in your handout, particularly the standards are available as a handout in your package. And with that, I'll close it up, and I'll be happy to try to answer any of your questions. Thank you.
Any questions for AJ?
I won't be here for the virtual grower thing tomorrow. I do have one question I've been wondering forever though.
Okay.
In regard to the perimeter insulation, it says either do between 1 and 2 inches and also 1 to 2 feet deep. And that seems to be common that I run into that. But there's a pretty big cost difference between the two, going from say a 1-inch insulation to a 2, and also it's double the material if you go 1 or 2 feet deep. So I'm just wondering if I'm comparing a 2 foot and a 2 inch to a 1 foot deep and a 1 inch, how can I better make a decision about that as far as what's being recommended?
So what you're really asking is if the cost that I have to spend, the money I have to spend to install these systems is worth the payback I'm getting in terms of energy savings. And I think you'd probably have to do a little bit more sophisticated analysis and probably looking at it over a longer period of time to really narrow down an answer to the question. In other words, I can't really give you a very good answer right now. It depends on the particular installation. It depends on the management of the greenhouse operation in order to come up to an answer. How much am I really saving? And as a result, is it worth going from a 1 inch to a 2 inch or from a 1 foot to a 2 feet deep system?
Is that what virtual grower will do? Will it?
No, I don't think virtual grower will give you that answer. No.
Okay.
It could. It may come.
We don't have the capacity right now to have the depth of the insulation,
Mm-hmm.
but we can have you select how high.
Okay. Well,
Yeah.
that'll help.
So, to give you a little bit more background about my answer, ideally we would do a research project and install different versions in a similar operation and do some measurements and figure out how much energy we're losing, and as a result try to come up with an answer that tells you, okay, in this case it would make sense to spend a little bit more money and go 2 feet deep, or no, it does not. But those kind of projects are relatively expensive, and within the current financial system in the extension service, it's very difficult to come up with that kind of money to do a really thorough research project.
Yeah.
On that same note, wouldn't it make sense to come up and cover that sill plate or whatever you want to call it, the lower structural foundation member, and come out of the ground an inch or 6 inches or however it's constructed, and cover that, come from the inside?
Yeah, that's what I showed you. Those panels on the greenhouse that was constructed, those were coming up maybe 3 or 4 feet high and extended, I think, one or 2 feet down into the soil. Yeah.
When there's all kind of residential data on covering the concrete slab foundation perimeter, which would be similar.
Yeah, except in residential buildings you often have basements, and that gets to deeper depths and then it changes. So it's not always, maybe not around here, but where I'm from, we have often basements, so it's different. So you may want to investigate and make sure you do the right type of calculation.
I think when you're working with a plastic structure, it's just a no-brainer to insulate the perimeter just because of the building materials that we're using. It's already leaky, it's already, it doesn't have that good of a U value, so I mean, it's just all in all, it just makes sense to insulate everything you can. The thing, going back to the insulating of the north wall, I mean, how much light are you really losing? Because, I mean, by the time, I guess it depends on how the house is laid out, but I would figure by the time that the sun got to that north end, then it would have been past its pretty much useful of its prime, if you will, of that day's sunlight.
So in our part of the world, the sun never gets to the north end, right? Because the sun doesn't get that high, even on the
right, because it's kind of coming up and going like that and setting. So I mean,
So the idea is that on cloudy days, like a day like today, sunlight is diffused in the atmosphere. It's bounced off all the water molecules mostly and other parts. And so some of the light will actually come in from the north because it was bounced around and then came back from that direction. Whereas on a clear day, the sun comes directionally only from the location of the sun, so it never comes from the north. So on those cloudy winter days, when the light conditions are really low, you want to have all the light available come into the greenhouse, including the light from the north wall. So if you put an opaque layer of insulation on the north wall, you block that, and you reduce the heat loss, but you block off that light from coming.
So if you looked at it from a calculation, would it save you more energy saving that heat than it would be, because you could put supplemental lighting in that end, right? I mean, you could possibly do that to kind of make up for that robbing of the sun. So that use of that kilowatt hour or whatever that energy unit is, be less or more than the heat saved from insulating that north end.
Well, I don't have hard data, but I would venture that using supplemental lighting would be more expensive than adding a little bit more insulation.
I think you could run that scenario in virtual reality.
Yeah, you might. Yeah.
That's what I'm talking about. I want to check it out.
I'll bring it up.
All right, guys, let's wrap this up then.